trying to unconfusing to a novice user, and macro is the word the manual uses when it lapses into computer science jargon. But they're the same, really, in concept, and probably the new manual will just say that we call them control sequences because they control TeX, and they're called macros because everybody programming computer knows what a macro is, and I don't know. Anyway, that's the. Now, on the other hand, for web, we also have macros, and we don't call those control sequences. We just call those macros. Those are things that have been defined with the define instruction in your book. Now, to represent a control sequence in TeX, there's that means backslash something is a control sequence, and the something is either, well, there's three kinds. One is where the something is one character long, and another case is where the something consists of two or more letters. And this letter means that the Checode, the type of the character in the Checode table is 11. That's what a letter means. So those are things that if you have two or more of those, that makes a control sequence in TeX, like backslash END. Then there's the third kind, which is an active character, and that's when the Checode is 13. And those are something like single character control sequence, but they're separate from the backslash. And so there was backslash ampersand would be different from ampersand if ampersand is Checoded 13 in TeX82, not in the old version of TeX, but in the new one. It makes a difference to the scanner also between those last two types. The control sequence starting with a backslash always ignores spaces that follow it. So an optional space always follows a control sequence starting with a backslash. But an active character, one of these code 13 kind of things, does not gobble up any space after it. So the space after that will survive it. Okay. Now in the inside the machine, we also have to take care of making sure that these control sequences can disappear at the end of a group if they've been defined inside of a group. And we have to, handle four kinds of control sequences that can be defined. They can be defined to be long or outer or both. Now, you remember long, it means that their parameters can take the end of a paragraph symbol. And an outer one is something that's supposed to be illegal to use except when you're at a quiet time, somehow in an outer part of the file, not within something else. Both of these ideas, long and outer, are intended to catch a common error of someone misplacing missing a right brace somehow, or not matching a parameter because of some typographic error. And instead of scanning all the way to the end of the file, we want to catch it real quick. So if you run into something that's outer, then you know you've made a mistake. So, for example, people will define something to be outer if it's the beginning of a theorem in a math paper. You shouldn't have a beginning of a theorem in the middle of some formula, right? You define something to be long if you expect that the parameter to that macro will possibly have more than one paragraph in it. But otherwise, as soon as somebody gets to the end of a paragraph and hasn't finished the argument to a macro, if the macro isn't long, then TeX will stop right there and recover. With some luck, it'll recover and go on to the next paragraph with a fresh slate. So we just mark those four kinds of control sequences: long, outer, or both, or neither. Question here? Please reach behind you for a microphone and push the red button. No, it has to go on the videotape. Push the red button.
Red button. Okay.
Yeah, wait a minute. Put your hand.
Do things like italics, \IT for italics, will they have to be declared to be long, or since they're equivalent to \:, something, will they automatically be long?
You see, they don't take a parameter, so it doesn't matter. It's only affects whether the parameter contains \PAR or not. Now, an empty line and \PAR are supposedly exactly equivalent. They should even match each other as parameters go. Okay, now when we've got a long control sequence defined in there, or macro, whatever you want to call it, we have to have a way to represent it inside a TeX, and this is the other important data structure that appears in MEM. These are all one-word items, and they're called token lists. And token lists are defined somewhere or other. Let's see, the table of contents, part 20 starts at module 270. So token lists are explained there with a bunch of definitions, but the real explanation starts on the next page. Well, you've got to turn the page back and forth on here. So what I wanted to do when I'm representing a token list is have something that in a half a word I'll be able to represent everything that TeX might want to be scanning. So I have 16 bits to work with, at least. Now, what do I actually get when I scan the letter A? I get a command code and a character code. So if I scan the letter A, I get an 11 and a character code, which is 65 for the internal code of a capital A. 11 is letter, and this is okay, but it's a number. You don't have to know these numbers. You don't have to memorize them or anything. If you were tracing with commands, it would say the letter A, because it would look at the command code 11, and it would look at the character code and figure out how to output its internal character code 65, and 11 would mean the letter. Now, command codes are very important, and we'll talk about those shortly. But within a token, they're restricted. They can only actually be between 1 and 14. None of the commands coming through in a token list are going to be 0, nor will they be greater than 14. And some of those aren't the same as the codes, and some of them are. I guess we might as well look at those first 14 codes. The command codes is a page that defines all these internal numbers. It's module 201. As I'm writing the TeX program, I'm actually referring to this page more often than any other page, but I don't think the reader has to. It's just that as writing it, I had to make sure that I had all the commands in there. Anyway, the small command codes that's in module 201, they're all they include the codes, and then we double use the ones that could never come through. So escape, for example, is 0, because if you give a code of 0 to a character, like a \, to make it an escape, that's the code. However, never will a with something with an escape code actually come through into a token list, because that starts a control sequence, and you're going to go ahead and get the whole control sequence. So that command code is also used to mean relax. And our left brace is code 1 is only left brace, 2 is right brace, and so on. And then we get number 5. If somebody had a carriage return, a character coded 5, that acts like an end of a line. And again, it will never come through the scanner, because we get to the end of a line, you look to the next line to get something and put a blank through the scanner. So 5 is also used to mean output a macro parameter. And it's also used to mean \CR. So it's got three purposes here. And for a character, it'll never come through. If you type a hash mark, that could come through as a 6. And so on with all these other ones. We get to an active character, a 13, it's going to be, again, a control sequence, so it's going to be replaced by something else. It won't come through the scanner as a token. But the end of a paragraph is going to come through as a 13, and so will something. Let's see, match a macro parameter. No, that'll be interrupted by actually matching the parameter. So end of paragraph, I guess, can come in as a 13. No, what happened? No, actually, let me see. Yeah, no, this 13 would come through, but it's only because it's stored inside a token list itself. So these 13 and 14 are special commands that are inserted into token lists just so that we can do our funny things with parameters when we're fetching them out of the scanner. And they never come through for user characters. Anyway, this command code will always be some number between 1 and 14, and none of the other values are possible there. This char code could be anything from 1 to 127, 0 to 127 for a character. And that's one case of a token. The other case of a token is a control sequence, like \relax is the simplest control sequence. But there are other. Can you see this far down? No, you can't see it. Yeah. Good idea. Okay, so now to get \relax coming through the token, we wouldn't give the command code for relax, but instead we'd give the hash table pointer for relax. Since between the time you define something with relax in it and the time you use it, you might have changed the meaning of relax. Or this might be some control sequence that wasn't even defined yet. So for this, we want to point to the table of equivalents for each identifier. So there's a hash table that a table that will associate with every sequence of letters that you've used. Somewhere relax will appear in there, and that will tell what the meaning of relax is. And there'll be a command code and a char code associated with relax at any given time. But in the token list, we'll just have a pointer to this word. We won't have the contents of this word, since this might change. So now, when we represent then a definition as a list of tokens, each token is either a pair of command and char like this, or it's a control sequence. Now, question, Toby?
The characters and the fonts are extended to 256, but these tokens are still limited to 127 characters?
In a font you can have 256 characters, but on your keyboard input, 7-bit codes are only accepted. So somebody does not, so we are not accepting 256 codes in the exchar array. The exchar array and the XORed array, exchar gives a let's suppose, for example, that we were on a cray where they have, I think, 9-bit characters, or say EBCDIC where you have 8-bit characters. Okay, let's say EBCDIC. So in that case, exchar of 65 would be some 8-bit character. XORed would be an array that takes any 8-bit character into a 7-bit internal code. But my internal codes are only 7-bit. For the things in the buffer, for example, in the string pool, are all 7-bit. So you have 128 internal codes that TeX would work with. That's not a terribly inherent restriction, except that if you wanted to work with larger, you'd have to increase the size of the code, the UC code, LC code, DEL code, SF code tables, because all of those are indexed by 0 to 127. But you would have room for, well, no, I don't add min quarter word to this guy either, I don't think. So you would have to, well, anyway, there would be room, though, because I actually compute the value of this token by taking 11, multiply by 256, and add 65. I compute the value of this token by taking a large number, sufficiently large, like 2 to the 10th or something. No, 2 to the 16th, 2 to the 12th, I guess. Because this will never be more than 14, so it certainly won't be 16. That would be 2 to the 4th times 2 to the 8th would be 2 to the 12th. So if I say 2 to the 12th plus the location of relax in the table will represent a control sequence. So we call this 2 to the 12th is called the CS token flag. And if you add CS token flag to the location of the control sequence, then you've represented the control sequence as a token. If you have anything less than 2 to the 12th, anything less than this token flag, then you divide by 256 and you figure out what the command and the character parts are of it. As far as extending the type ASCII code to 8 bits, this would lead to incompatibilities with other versions of TeX. Yet I don't think it would mess up any of the data structures particularly. One character Webb says that one character constants are used for strings 0 to 127, and that would also have to be changed to allow one character constants to be larger, because Webb's internal code is identical to TeX. When you say double quote A in double quote in a Webb program, it's supposed to give the same internal code that TeX uses. The internal code is, of course, just internal. So you know it's an arbitrary mapping. If we can handle EBCDIC, we can handle anything. But as long as it only maps, as long as it only gives us 128 different possibilities on in, then we can move those 128 into 256 or 512 afterwards. But we just won't fill the whole range. Now so the data representation of tokens, as I've said, has two cases because there's two kinds of tokens. There's the control sequence tokens. This includes all three kinds of control sequences because all three of them are located in the same array, or the kind that are packed with a command and a character together. Now, in order to demonstrate, so let's see. In order to demonstrate that, again, there's a procedure called show token list, and that starts in module 273, and it's just 2 pages long, but it goes through and interprets a token, a whole token list, and that's what prints out a lot of the things that you would see in TeX when you have when it's showing you what it thinks a macro was. It's using this show token list procedure. Now, there's some more complications, though, that I've got to mention because of parameters. You see, a token list has to also represent the fact that a macro might have parameters that we want to match, and so that's all explained in module 272. And there's an example there, which I might as well put on the blackboard, but it's also in there. It's also in the note. Now, the example is a definition of a macro, and we're just going to show how that's represented inside step by step so you get the idea. So somebody has typed into TeX define \mac a #1 #2 space, and then \b, and then a space. Space, of course, will be ignored since it follows a control sequence. Then left brace #1 \-a space #1. This is not intended to be the simple example. This is intended to be the one that shows you everything, so that you'll be completely puzzled at first. But if you have a little patience, you'll feel that nothing. Once you figure this one out, then you'll feel that you have total power to do all the rest. Now, this example is shows all the kinds of things that can happen, except for matching a left brace, which is a slightly special case. Now, okay, Mac is going to be a token list inside of TeX, and and it's going to be in that one-word area of memory, linked together, and the info parts of each word is going to be a representation of the token. So let's see what it would look like. Well, first of all, you would have a letter and A. That's type of 11, but let's write it symbolically. So letter A, that's the first one. Then you have a parameter, number 1. Now, you don't store that as hash mark 1. Well, for one thing, the 1 is redundant because the first parameter has to be number 1. So instead, it just says match a parameter, and it doesn't give any number in it at all, but it does give the internal code number of the hash mark, because somebody might have several different symbols that he's using for macro parameters, whatever type that is, 6 or something, and whichever one he used, we could reflect there and type it out in that as that character if we are asked to type out this token list. So we save that character there. We call it match. But then the 1 is suppressed. If the person wrote 2 here, give them an error message saying, illegal, you're supposed to number your parameters consecutively or something like that, and then that would catch an error of where something else probably was wrong up above. Now matching, these two go into just match and duplicating the character code, internal code of this guy. Similarly for that one. And then a blank space. A blank space is type spacer in the command code, and the code for space. I can mention that all space codes, no matter what the character is, if it's a type spacer, I convert it to a blank on input, so that they'll all match each other when you're matching macro parameters. A carriage return, a tab, anything that you've set as a type space will match in a macro, and the reason is that this had caused many errors where people were trying to would make a definition, and they would in one place have a carriage return, in another place have a space or a tab or something, and it would look okay on their screen and say, what's going wrong? So everything that's been defined to be of type spacer is actually converted. TeX doesn't remember anymore what this spacer was. If it was an asterisk and somebody said asterisk was code 10, it would just be equivalent to a space. Then comes letter. No. That's ridiculous. That's a bug. Okay. Well, that's a bug in the comment there. This would be a control sequence B. So this would be, this would be control sequence. So this would be CS flag plus the location of B. Is the next thing, and so I guess, in other words, I can represent that notationally as just \B. So cross off the word letter there. That's a misprint in that line. You should just say \B. It's a control sequence for B is the next thing after this blank space, and then no blank space for that. Well, then comes a special token called end match, and end match is the command code at and the chur is 0, I believe. So the end match is a command code of 14, and match is a command code 13, I guess. And and this tells TeX that when you're trying to look for Mac, then you get here, you finished, you got all your parameters. Now, proceeding then, we would go into the first thing, and this would say out param 1. This would say it's time, as we're continuing to read this token list, to now start reading parameter 1 that we've already found as we've been reading this part of the token list. And then it would say, do this control sequence, and it would say letter A, and it would say blank space, and it would say what? Well, now, in a right-hand side of a definition, 2 hash marks in a row is used to stand for a hash mark. So this would now say macro parameter hash mark. And then this is a other char 1. It's not a letter, and digits aren't specially noted, so this is a 1 of type 12. This is parameter 2, so it's out param 2, blank space, significant, after a digit, usually not significant, because a digit is usually a constant, but in case of parameters, parameters are only 1 digit long. This space is there, blank space, and again, out param 2. And then the link of this last token will be 0, or will be null, I mean, indicating that the token list is over with. Okay? So inside of TeX, there would be this list of half-word numbers, and you ask the show token list procedure to print these, and it would print what? Well, what it prints is shown on the example of the next page on 273. It prints the letter A, then it prints hash mark 1. Now it knows what your character is. It knows what your hash mark character is by looking here. It learns it as it goes because you might have used some other symbol, and TeX isn't initialized to think that this character is any different than any others. And different token lists might have different hash characters in them. And then hash 2 comes out, blank space comes out, and control sequence B. Now, whenever a control sequence ends with a letter, this show token list automatically puts a space after it. Just in case the thing after it is going to be a letter. It doesn't look ahead to see if a letter is next. If a letter were next, it would be a bad mistake to leave a space out. So there's always a space after this if it's a letter. I think maybe even if it's not a letter, I forget now. In the old TeX, it made a decision, but I think now it always puts a space out, but I don't remember for sure. And then it gets to end match, and it translates that into a hyphen and a greater than sign to look something like a right arrow. Then comes out param 1 gets translated into hash 1. Okay. Presumably you're not using out param unless you've already had parameters, so it's already learned what code to use for that parameter. However, I think it can learn always in time. So it puts this out, and it says there's no space after it, so I have to double check the code and see if it does that or not. It says backslash hyphen without a space, and I'm not sure about that. I'll double check it. Then letter A, space, macro parameter, that comes out as 2 of those symbols. 1 comes out as a 1, and so on to the end. Now let me see, so let's see if we can figure out from this code what comes out when I'm displaying a control sequence. So the token list procedure looks like this. I'm reading from module 273. It's got several parameters. The P is the main one. That's where the token list starts. Q is another one that's only used if we're printing out error messages. If we get to position Q, we're supposed to do something to switch from line 1 to line 2 of the error message. And L is an upper bound. If we get to printing out too much output, we'll quit. No sense going any further than that upper bound. Okay, now come into the program, and it sets matcher to hash mark just in case we haven't learned it in time. I think that's only to make this procedure robust in case of a token list that wouldn't really have arisen in the course of a TeX job. N is 0. That's the number of parameters we've seen so far, and tally is the number of characters we've generated. Okay, now, so the main thing we have to do is display token P and return if there are problems. So that's module 274. Let's look at 274. if P is out of range, then we print escape clobbered with a period after it. So we're debugging, and you're printing out a token list, and you get to a pointer that it's not in the one word area of memory. Then something is definitely wrong, and we're going to give up. We're going to print clobbered with a period after it. We can tell that distinct from the control sequence clobbered. Because why? Because if the user had a real control sequence clobbered, it would also have get a space after it instead of a period. So this way, at least we'll be able to look at the message and see that it was this kind of error indication. But this procedure is not supposed to ever call error because it's used by the error routine to describe the location of an error. Okay, now if info P is greater than or equal to CS token flag, then we're in this case where we have a control sequence, so we call on our subroutine called print CS, which prints a control sequence. Otherwise, we're going to divide by octal 400, or same as saying 256, and break it into the M and C part. The M is the command code, and the C is the character code. We print bad with a period after it if we happen to have a negative token for some reason, or a character code greater than 127. Otherwise, we are going to display it in the fashion described on the next page. Okay, so we got to, in order to solve our problem as to whether a space comes after this or not, we have to look up print CS. Where in the heck is print CS? Well, for that, I got to look in the index. Now, sometimes I thought it would be neat to have a subscript on all my identifiers saying where they were defined, so I could save one step in my search. Excuse me? 245? Okay, thank you. Trouble with that is that some identifiers are declared many times, and so I would have to know about the scope of each one, and it would be quite tricky. Now, okay, print CS, it says it prints the name of a control sequence and a space after the name if it consists entirely of letters. And so that's the idea here. Then it will not get a space after this backslash hyphen, and this hyphen had been coded to be of type letter. And it goes through the three cases of a control sequence. Now, here we get. I want to talk about another one of TeX big tables. This is the table called the table of equivalence, and the table of equivalence is where we keep all of the meanings of all the control sequences. The table of equivalence is described starting on module 213, and it's called EQTB. It's one of the few places where I've used a cryptic abbreviation instead of a word or something unpronounceable as an identifier in this program. I used to do that a lot, and now having the freedom to use multi-letter identifiers, it turned out usually better to have a long pronounceable identifier. But this darn one was used so often, I couldn't see myself writing out equivalence table, and I couldn't think of a good in between. So it's called EQTB, and I don't know what I say to myself except ICTIB or something like that. When I read it, I'm sorry about it. But anyway, there's 6 parts to EQTB. And they aren't equal size, but I'll just pretend they are for the time being. So there's 6 regions, and let's take a look at what they are. Now, the first region is one character control sequences. So these are the things that there's 128 of them that could be active characters, type 13 characters, and then there's 128 of them that is backslash character, backslash A, backslash hyphen, and so on. So 256 altogether, one character control sequences. The next region is the greater than or equal to letter control sequences. The third region is for skips and glue parameters. Fourth region is what I called, well, half-word entries, but it's like local quantities. But it's half-word entry, things like the name of the current font, the name of the current par shape, and all of the boxes, like box 1 or box 0 up to box 255, pointers to those boxes. Pointer is a half-word, so boxes are now local. They'll go away at the end of a group unless you define them to be global when you said set box. And so anyway, it's put into EQTB. Then these are integers here, and the last are the dimensions. So it has 6 parts to it, and it's used for keeping local quantities. Everything that I want to be subject to the local mechanism, the thing of going away at the end of a group, is stored in EQTB. Now, especially the control sequences. Now, for these entries in regions 1 to 4, it's funny, it has 6 regions, and they're slightly different in their feature, but one thing they have in common is that they are going away at the end of a group. Now, in the first 4 regions, for each guy in here, we store a command and a modifier called the chur to the thing. The command is a quarter word, and the chur is a half word. So every control sequence, for example, has a command that indicates whether it's a ordinary call or a long one or an outer one or a long and outer. Or it might be a TeX primitive, so it might have a command code that says this is a def instruction or something like that. So the command code says what this control sequence means. The chur code is a half word, so it might, for example, in the case of a defined control sequence by the user, H would be a pointer to the mem location for the beginning of the token list. Well, it's not really the beginning of the token list because there's a reference count first. For each token list, we keep a count of how many times people are using the token list. Whenever that count drops to 0, we flush it. This has turned out to be quite an efficient way to do things. So it's a pointer to the reference count of a token list in the case of a call instruction. But it's a half word. The chur field is a half word. And you have these for all 4 parts. That's what the equivalent is. This is called, the command field is actually called the EQ type, and this part is called the equiv. And then later on, if TeX is using it through the scanner, EQ type gets called the command, and equiv gets called the chur. Some of the EQ types are special that should never come through the scanner. For example, the current paragraph shape is stored somewhere in this region here, and its EQ type says par shape. And but par shape, when it comes through the scanner, it's not supposed to mean the current paragraph shape. It's supposed to mean the command to set the paragraph shape. It's a different thing entirely. So par shape here means to TeX this equivalent has to be recycled in a funny way. When you're coming to the end of a group and you're going to give up this par shape and go back to the outer one, you have to return a par shape node to the free memory. And that's why you look at the EQ type to see that. So some of the EQ types are command codes that would come through the scanner. Some of them aren't. But in any case, all of these guys have a type indicating what kind of equivalent it has. Now here, in the last 2 regions, though, they don't have a quarter word and a half word associated with them. They have a full word, an integer, or a scaled value, of course, because an integer wouldn't fit in a quarter word and a half word. So in those regions, when we fetch a word out of region 5 of EQTB, we expect to take a whole integer out of it. Now region 2 is special because it has a hash table associated with it. All of these guys, furthermore, have a hash array that runs from the beginning of region 2 to the end of region 2. And the hash array will give information as to what's the name. What are the letters in this thing? So they have pointers here, and one of them is a pointer to the string table. It's the number of a string, so we can say where the name starts in the string pool. The other one is a pointer within the hash table to other things that belong to the same list. We take the letter sequence and convert it to a small number, and then everything that has the same value of that number would get linked together. The method actually used for hashing is called the method of coalescing lists, and with the refinement that my student Jeff Vitter wrote a thesis about, so that we actually choose this hash value that we take every sequence and we convert it to its so-called hash code, which is a number somewhere about the first 85% of this table, and the first things when we have two things going into the same place, the first ones go into the last 15% and start filling up the table until finally the overflows come into the main table itself. And Jeff's thesis showed that 85% is the right number to get the best efficiency out of this method. You can expect that these lists on the average are going to be of length something like 1.7 or some small number, so that very rarely do you actually have a long number of things to check. Those are details about hashing that are in another book I wrote. Anyway, that's a hash method. But the hash table, then, an array called hash, starts at location at the beginning of region 2 here and ends at the end of region 2. It's only used for that part of the table. Now, these equivalents, then, are where we keep control sequences. So let's recapitulate what I said. Suppose somebody says def A, and then he puts B here. Okay, it's a fairly simple case. So what's going to happen? TeX is going to look to see this backslash here. It says, escape character. It's going to be a control sequence, and it looks at the DEF, and then it sees a non-letter, and so it says, okay, DEF is the thing I'm supposed to look for. It's a control sequence made up of more than one letter. So it computes a hash code for DEF. Say the hash code is 300. It looks at position 300 and points to a string and says, does that string number 3, string indicated by this, is that DEF? Whoops, no, it isn't. It wasn't DEF. Okay, we'll look at the link here, and we'll look at another place in the hash table that points us to another string. Yes, that is DEF. Okay, so we found DEF at this part of the EQTB. What does it mean? So we look up EQ type of DEF, and it says that's define. That means you're defining a control sequence. And so you found DEF that it means define. Okay, the define routine looks at the next token without expanding it as a macro, and what happens? It sees an escape sequence. It sees a letter. So it says, maybe there's going to be another letter. We'll have another control sequence of more than one letter. No, it's not a letter. It's to code 1. It's a left brace kind of a token. So this is a one-letter control sequence. Special case of a one-character control sequence. So we look up here. We don't go through hashing on this one. We pick it up out of EQTB, and we look up here. What's its EQ type? But we're going to define it. So no matter what its EQ type was, if it could have been def also. It could have said define. Whatever its EQ type was, we're going to change it and make a new definition of it. We're going to put in this place in EQTB call, which is the command code, the EQ type for an ordinary defined control sequence. And then we're going to run a little program that's called scan TOKES that reads the left brace, goes to the end, builds a token list for this thing, puts it in a big memory array, and then the equiv is going to point to that token list. And we'll have a call in here. Now, but what about what used to be in there? Before I put the call on there, A was defined as something else. I've got to do something with that because it's got to come back again later on when I get to the end of the group. Okay? So that's the last link in our chain here. And there's another table of importance called the save stack. And this is where we save things that have to be restored later. So the save stack is full of memory words that are going to be put back on EQTB later. Let's see now. \A is in location. If you work it out, it's 129 plus 6 plus 97, whatever. Well, whatever. Let's say, might as well get it right. 226, I think. In location 226, there's going to be \A, and so it's going to be represented as location 226 in EQTB. Now, when I'm redefining that, there was a previous meaning to \A. I don't care what it was. Let's call it star because it just whatever its previous meaning was. When I define it again, this previous meaning is going to be wiped out, except that if I'm inside of a group, at the end of the group, the previous meaning is supposed to come back. So what I'll do is, in the save stack, maybe the save stack already has some stuff in it. Here I'm going to put the old thing that used to be for A, and then on the next word under it, I'll put 226, indication that 226 has to be fixed up when I get to the end of the group. Okay? So the save stack contains a lot of two-word items like this. And the 226 also has a type code associated with it saying fix up 226, okay, something like that. Now, usually when I'm doing this control sequence didn't have any meaning on, it was just an undefined control sequence outside in the outer block. And so I'm wasting space on the save stack, so there's a special case, it says easy fix up, or whatever it's called, in the case that this star was the most common one of undefined control sequence. And easy fix up, it'll only store one word and assume that the previous one was easy fix up. But that's a technicality. Conceptually, it's the same idea. There's just a small refinement to it to save space. So what we put in then when we change something on the EQ table, we put an entry on the save stack. And this will be the address in EQTB. And if the address is one of these high numbers, we know that the thing we have to restore is going to be an integer or a scale or a skip or a half word or something. By the range of this address, we can tell what kind of a fix-up we're going to be doing. If it's a small number, we have to look at the EQ type to see what kind of a fix-up we're doing. But if it's a large number, we know it's an integer. Yeah. Please use the mic.
How do you know how much to restore if you have nested braces down to several levels so that you don't want to restore everything?
Yeah, good question. See, we have to store more information. You pointed out that my data structure is incomplete, but fortunately there's room for another quarter word here. Because I had a half word and a quarter word, yes. I have another thing called EQ level, which is the level at which thing was defined. And this is important because if I didn't have that, I wouldn't be able to do it right. So now besides this, I have a level, and this is the level at which the definition was made. And then this number is a little tricky. You have to work it out. And in fact, in the first version of TeX, I think about 6 bugs were in that section because I kept learning more and more about this scheme and each time I thought I finally understood it completely. Now I think I do, but I'm not sure I can explain it to you in 5 minutes. But there is a level at which the definition is made. And so level goes in with it, and if this level turned out to be the same as the current level, then I don't even bother putting anything on the save stack, because the previous definition, because something already was saved from an outer level. So suppose, for example, I'm on level 3, inside of 3 pairs of braces, and I have 2 depths of A. When I did the first depth of A, then I saved something for fixing up later. I did the second depth of A, I just throw away the first depth. I don't have to store away the first depth. If I stored it away, it would take up space, and I would undo it, and then I would undo that again. So there's no point in wasting the space and doing extra work. So I just throw it away at the time if it's the same level. But if it's at a different level, actually I must be at a higher level, because it is going to be a property of this whole method that every level on the save stack is less than or equal to my current level. I think strictly less than my current level. So I'll never save anything. And when I restore the save stack, I'm going to, when I get to the end of a group, I'm going to pop back until I get to the right place in the save stack. So besides fix-up words in the save stack, I might have another fix-up word here. And then I'll have a boundary type of a word here. Okay? A boundary type of a word that says, this is where I began a new group. And there will be a boundary word up here too. Beginning of a new group. Okay? So when I get to a right brace at the end of a group, I run back and I do all the fix-ups until I get back to the preceding boundary. And now everything is restored to the way it was when I entered that group. You get the general idea of this method? So when I get to the beginning of when I get to the start of a group, suppose somebody writes HBox and then left brace. Okay, I'm beginning a group. So everything in here, when I get to the right brace, it's going to tell me, then I'm going to go back and restore all the definitions of things that were made in this group, and that'll be indicated in this boundary here. Now, I need a few more pieces in my data structure, and you're probably going to discover this, yes? No? Okay. Now, the way the old version of TeX, this is a big change between the old version of TeX and the new one, and why the new one can be a lot better. The old way was that I kept in this boundary word here what kind of a group was starting there. For example, in this HBox case, this would say beginning of an HBox. But I didn't remember what kind of a group I was in. Instead, I would go through, do all my fix-ups until I got back to a boundary word, and it would say, oh, that was an HBox group that you were doing. So a right brace came along, but at this point I had forgotten really what kind of a thing I was working on, but I knew it was somewhere in the save stack. And so I just went back to it, and then it told me, yes, it was an HBox group, and so then I go and finish the HBox. Now for TeX82, this would be very bad, because if we wanted to get rid of HBox par and things. So if this was a VBox, and if I would destroy all this stuff here, I would be about to make a paragraph, but I've just erased the baseline skip that I was supposed to use for that paragraph. So I want to know when I have this right brace that I'm in a VBox, and still have to finish that before I go doing these fix-ups. So the new data structure I keep track of what kind of group I'm in. It's called cur group, the kind of group I'm in. And then in the boundary word, I don't store the kind of group that was starting there, but the kind of group I interrupted. So this boundary word is going to be a pointer to the previous boundary word, and it tells what kind of boundary word that was. Therefore, when I get to the end of a boundary, when I get to a right brace, I look at cur group and says, oh yes, I'm finishing I'm finishing such and such a kind of group, and if I want to, I can do these fix-ups. As soon as at the right time, I can do the fix-ups. Then I finally do the fix-ups. Then I set cur group to the old cur group that was stored there, and resume as I had it. So the saving and restoring equivalence gets a bit subtle, and it's all described in let's see, part 19 of the program starting at module 251. So the problem of saving and restoring equivalence in that part of the data structure is discussed there, and it's one of the most subtle parts of TeX. The program is actually short. It covers modules 251 up to 269. So it's a rather small amount of code, but the code itself had to be just right in order to do all these features. I haven't described what about global definitions yet, and that's the other interesting thing about this, which you add on top of everything else I said. What happens when you said global or GDEF of A? And in that case, you don't bother saving the old value because you're never going to want to put it back again, and you set the EQ level to 1. And if you look carefully at what this does, and you have to consider all the cases where you have, say, 10 definitions, and some of them were local and some were global, and see exactly what gets stored and what didn't, you'll see that it does, in fact, work. So that's the other catch, is that when something is global and I try to fix it up, I'm coming through in a right brace and I try to fix up something, and I look and see that the thing that's in there is at level 1, that means it was defined global in the block, so I don't really fix it up at all. And Yep. Dan?
Is there any other use for EQ level besides that?
No. Well, it's important for garbage collection because if I didn't know that, then I wouldn't throw away things at the wrong time, at the right time. I would lose my last reference to a token list. So that's why I have added an extra quarter-word array called XEQ level here to regions 5 and 6, so that I can have the level information for these two guys which didn't have an extra quarter word. So regions 5 and 6, there's extra arrays of 1 byte each for these guys saying what their level is. Without that, things would go wrong. At one point I thought I could get by with it, but then I found out later that I couldn't. So I needed all the structure of levels and boundary and so on. It's all wrapped up, and if any one of those things goes, the whole thing falls in some cases, even though it might work for a few months. This is the way. This kind of thing can actually work on all the simple examples, and then it'll fail on the others. So now I believe it's been thought through with perfect rigor. But it was one of the subtle parts of the program worth studying, I think, for software people. Okay, that's the then representation of control sequences and equivalence, and the subtle parts about it were related really to the garbage collection issues that I just hinted at. Namely, there's a reference count on each token list. So suppose I've saved something on the stack. Suppose I've saved this, and this was a pointer to some place in memory, the old definition of A. All right. So that token list has a reference count associated with it. Now, I did a def of A. Well, then later on in this block, I did a gdef of A. So at that point, I wipe out this definition. I set the level to 1. But later on, but this fix-up is still there in save stack. I'm not going to go back looking through the save stack to see if I had any fix-ups for the thing. So then when I finally get to the right brace and I come through, I see fix-up 226. I look and see, oh, the level's been 1, so there's been a gdef to this guy. I'm not going to fix it up. I have to remember to decrease this reference count on this entry that I'm not going to use. I don't just ignore this one. I decrease its reference count. That was one of the latter bugs that I caught. That I had been losing my memory at one point because of this. Yes, I'm forgetting all these things. Losing space in my memory. Okay. I wanted to make a point about this a little bit, that at level 1, at the outermost level, you don't have to save anything because there's never going to be a right brace getting you out of that level. And so you save yourself. That's why people have had the phenomenon that TeX will work fine on a program, and then they put left brace and right brace around everything, and all of a sudden it runs out because save stack overflowed. The reason is that when you're in level 2, when you're inside of braces, then I'm starting to having to save everything. And in the old TeX, it saved every time you changed the font. Every time you change current font, it put something on the save stack. Pretty soon, if you had a long enough program, the save stack would have lots of fix-up fonts in there. Well, now it not only, I don't think it will change the font anymore because I have level on the font I didn't used to, but I have, it still will use memory more efficiently if you don't have unnecessary braces here. Okay. Now, some other questions? Yes.
If you have a definition in the outer level, then it would be.
I can't hear you. Sorry.
Sorry. If you had a definition in the outer level, say a /A, then it would have level 1. And
okay.
then,
Yeah. Level 1 is what inside the program when it's level 1 is the technical term used for the outer level, because level 0 is completely undefined, and so we consider that an undefined control sequence was defined at level 0. That's a technical point. When I send an error message to a user, I say he's at level 0 when I think he's at what I call level 1, because he's not really inside of any braces. So, for example, suppose you write this TeX program, left brace end. When I see the left brace, I set cur level. It's one of my parameters. One of my global variables is cur level. When I see a left brace, cur level goes up from level 1 to level 2. Then I see end, and I check, is cur level greater than level 1? And I say, oh yes, it's level 2. This looks strange. So I tell the user, end occurred at level 1. It doesn't use the word level, though. I fixed the error message so it's a little more, makes a little more sense. It says 1 instead of 2, even though the number inside of TeX is 2. I report it to the user as 1. If you want to understand what I'm talking about, it's all much clearer if you look it up in the code. And end occurred, that's module 1203. When you're just finishing TeX, one of the last things it does is it gives this message, and it said end occurred inside a group at level, and then it prints out cur level minus level 1. If you can think of a more informative error message than that seemed to be one that my wife understood. It's my test.
excuse me, then.
You have it? Yeah.
Does it work? Yeah. What happens if on the outer level you have a /def, you have a def/a, the second level you redefine it, and the third level you gdef it?
Okay, yeah, let's look at this case just to see what happened. So here I said gdef a, okay? Yeah, so on the outer level I defined a. Nothing goes in the save stack because its previous definition was, I'm still at level 1, so nothing is in the save stack here. There's no way to take this one away. It'll never end at a group, so I never put anything on the save stack for that. Here, I put something on the save stack, and so this will be then, what was it, 200 and whatever. 2 what? 226, okay, and it'll say fix up 226. Let's call this, okay, alpha, beta, and gamma, okay. So after I do this definition, I stick alpha in here. When I get to this definition, it'll say fix up 226 alpha, and beta gets stuck in here. When I get to this definition, and also this will say level 2, okay? And this will say 1 alpha. Okay. Now I get to this definition. I'm at level 3, so it's not equal to this level. So I put it on the save stack. 2 beta, fix up 226, and put in here 1 gamma, GDEF, 1 gamma. Okay, get to the end of this group. What?
Why do you put on the save stack since it was a GDEF?
You're right. I didn't put this on. So it was a GDEF. Yeah, that's right. I didn't put it on. I just wiped it out and decreased the reference count to beta. Then, then when I get to the right brace here, I look back and I see it's going to, no, nothing happens. I get to the next right brace that finishes this group, and that'll tell me to fix up this definition here. But I look in position 226 and it's got a global in it. And so that's, so it doesn't get fixed up. Now, on the other hand, if somebody had made a def of A at this point, then it would have something at level 2, and I would go back, and that would have wiped out the GDEF at this point. You see, so it's the last GDEF survives, but it can be a GDEF can always be canceled by a local def, and this one would store away this guy, gamma, and then that gamma would be restored. And when I finally got, and so finally when I got to this one, it would still not replace gamma by alpha. That's what I meant by saying try it, and you'll see that it works. And besides, there's an informal rendering of the proper invariant relation that gives the basis for the mathematical proof that it works, stated in that section there. What was it, 250 something or other? I believe somewhere I at least hinted at what was the right notion of it. Let's see. New save level. Well, I can't find it just now. Well, yeah, 265. If at least one global definition of EQTB has been carried out within the group that just ended, the last such definition will therefore survive. And that, if you translate that into quantifiers and logic and everything, would be the right thing to put in a formal proof of correctness of this algorithm. There's another complication that I didn't mention, of course, with respect to if, so when you say if, then the level number doesn't actually go up when you pass this left brace. And so when you get to the right brace afterwards, you just take out the boundary word and shift everything down. You have to read the code, but you'll see that it works. Okay, any more questions? Well, tomorrow morning then, we begin the class at 9:30, and we begin breakfast at about 9 o'clock, so come early enough and have some to eat.
What are you trying to
Start at the beginning, I would say, and start at the beginning, read some of these comments, and familiarize yourself with the use of the index, and then set yourself some problem or other. In other words, something, say, I wonder how he does that. Now, the way you can do that, that's a good question. If you take any one of TeX primitives, like def or something like that, you can look it up in the index under that name, and it'll say def primitive. It'll refer you to the place where it was put in the hash table, and then that'll refer you to what command code it has, and you might be able to trace through, looking at the index, the whole history of def, how it comes through TeX. But anyway, give yourself, if you don't like that problem, give yourself some other little task, saying, I wonder what this what this does, and that'll just give you a reason for perusing the index and finding your way through the report. Because the main thing to do is just to get a little familiar with the notation and mess up the page, get the pages a little black on the edges. Yeah.